telling you about some recent work on sparsifying suprema of Gaussian processes. It's joint work with collaborators Anindya, Shivam Nadimpalli, and Ryan O'Donnell. So it's going to be about Gaussian processes. Most of the talk will take place over, Rn, where we're thinking about the Gaussian measure, the standard n01 to the n Gaussian distribution. Before I get to talking about Gaussian processes, I want to tell you how we sort of arrived at the main result, which was we were thinking about a problem that has to do with sparsifying convex sets under the Gaussian distribution. Okay? So I'll tell you about that problem. We'll see the connection between sparsifying convex sets and sparsifying suprema of Gaussian processes. I'll tell you about the main result, and it has a number of consequences that I find kind of interesting, so I'll go into those. And the last part of the talk, I'll tell you some ingredients of the proof. I won't give the entire proof. Okay, so I'm going to start off by telling you about this question about sparsifying convex sets, which was our initial motivation. In turn, to kind of arrive at that question about sparsifying convex sets, we were motivated by a question about discrete space, the Boolean hypercube. This is a well-studied problem known as CNF sparsification. So I'll start kind of 2 steps before the beginning and tell you about that. Okay, so let's remind ourselves what CNF formulas are over the Boolean cube, 0, 1 to the n. Very, very simple class of logical formulas. A CNF formula, you can think of it as like a depth 2 circuit. There's an AND gate on top, large fan-in, it's got ORs of Boolean literals down below it. So here's an extremely simple example of a CNF formula. The first OR is satisfied, and the second OR is satisfied, and the third OR is satisfied, the function would output 1. We can, of course, think of such a formula as identifying a subset of the Boolean cube, the subset of assignments that are accepted by the formula. Okay? Some terminology is going to be useful. We say the size of a CNF formula is the number of clauses, these OR gates that it contains. So this would be a CNF formula of size 3. It's got these 3 OR gates. And the width of a CNF formula is just the maximum number of variables in any clause, how wide each one of these individual ORs can be. I should mention, this is a very unusual CNF formula. I guess it has size 3 clauses, and width 4. The first of the clauses has 4 literals in it. We usually think of the width of a formula as being much smaller than the size of a CNF formula.
Sorry, x11 is what?
Excuse me, x1 with the
one, the last one.
Oh, that's the negation symbol? It means 11.
It's 11.
Oh, that's 11. Maybe I should have stuck to single-digit numbers. Good. Okay, so here's a very simple folklore result. I should say the entire talk is going to be about approximation. We should be in an approximation mindset. We're trying to maybe get this Boolean formula right on 99% of all 2 to the n inputs in the cube, or we're trying to get some convex set approximated under 99% of inputs drawn from the Gaussian distribution. So we're in an approximation mindset. For now, we're over the Boolean cube. Here's a very simple folklore result. Suppose you've got a Boolean function, which is computed by a size S CNF, so S clauses. Okay? Well, then there's a CNF formula which is quite narrow, which has width at most log S over epsilon. Every clause has just this logarithmic number of literals in it, which is epsilon close to F. And by epsilon close, I just mean that these 2 formulas, F and F prime, agree on 1 minus epsilon fraction of all inputs. Okay? So again, whenever I talk about the Boolean cube approximation, we think about the kind of distance between functions is just under the uniform measure. Okay? So this has a 1-line argument. All you have to do is start with the original formula, and if you see a clause that's too wide, wider than log S over epsilon, cross it off, throw it away. Okay? Every such clause that you cross off will only, change the value of the function. Throwing it away only changes the function on an epsilon over S fraction of all inputs, so you do a union bound over all S clauses, and you see that you've changed the function by crossing off these clauses on almost an epsilon fraction of all inputs. Okay? So the punchline here is that small CNFs, if the size is not too large, are essentially narrow. They can be approximated by narrow formulas.
So the size is also smaller than S, right?
Yeah, the size would only go down. It's a sub-formula, in fact. Exactly. So this is a very simple result, not so interesting, but we might ask, what about a converse? Does something like this hold in the other direction? And that turns out to be a much more interesting and richer problem. So we can formulate this as follows. Suppose I give you a narrow CNF, a CNF computed where each of the clauses has width at most W. Okay? A priori, a CNF like this might have many clauses. It might have n to the W or something like that, many clauses. But maybe that's overkill. If we only want to get it right on 1 minus epsilon fraction of the cube, 99% of the points, can I sparsify? Can I somehow make it much smaller? Let's maybe go through this in a very simple case. Let's think about the case where the width is 1. So with 1 CNF, every clause has just 1 literal in it. In other words, it's just an AND of literals. Well, you can see that here, if you're only concerned with epsilon approximation, there's no reason to have a number of clauses which depends on n. In fact, if you have more than log 1 over epsilon many clauses, the function will be epsilon close to the constant 0 function, right? And we can just approximate it trivially as a and of two literals, x1 and not x1, okay? So in the case w equals 1, we can epsilon approximate any CNF formula with just log 1 over epsilon size, completely independent of the ambient number of variables n. And this gets us thinking, right? Could it be the case that for every, think of it as like a constant w, given any width w CNF, perhaps it's close to a small CNF. The CNF whose size, again, depends only on that width parameter and the approximation parameter, but is independent of n. A reasonable question. If we had a result like this, we could call this a CNF sparsification result. We go from a big CNF and prune it down dramatically to like a constant size CNF, as long as it was had a small width. Okay, makes sense so far? Good, so I won't keep you in suspense. This is a completely solved problem in the Boolean setting. The first result along these lines was due to Luca Trevisan about 20 years ago. He gave a result which was of this flavor, essentially a sparsification kind of result using a fairly large number of clauses, and it's done really with a one-paragraph proof. It's an extremely simple kind of packing, covering argument. You look for a maximal set of disjoint clauses, snarf them all up, do a restriction, and recurse. It's a very elegant, nice argument. So people thought more about this kind of result in subsequent years using more sophisticated technology. Gopalan, Mecca, Reingold employed these kind of quasi-sunflower objects from combinatorics to give a better sparsification result using fewer clauses. Levet and Zhang used tools from Boolean function analysis, noise stability, these combinatorial switching lemmas to get a kind of different trade-off between the parameters. And finally, an optimal result was proved by, I think, Levet, Wu, and Zhang. This is really kind of a sharp bound up to the constant and the exponent on the number of clauses you need to do this kind of sparsification. And again, it's using these kind of Boolean function techniques, not surprisingly. Okay? So in the CNF setting, this discrete setting, the sparsification problem has been solved. That's great. Okay, we're going to leave the Boolean cube behind, and for the rest of the talk, I'll be talking about the Gaussian distribution over Rn. Yeah?
Sorry, just out of curiosity, so are you asking for something algorithmic also? Does f prime have to be computed in an efficient way out of f?
I'd have to go back and look. I think it is efficiently computable. In fact, it's even efficient. You can do it efficiently even in kind of an implicit sense if you only get black box access to f and not the explicit description of the function. Yeah. But for most of my talk, I'll just be talking about existential stuff. You can make it efficiently computable, although in some sense the input could be an infinite-sized object in the setting we'll consider, so it makes my head hurt, and I don't want to think too much about that. We should be thinking just kind of existentially for the rest of the talk. Yeah, that's a good question. Okay, good. So for the rest of the talk, we're going to be over kind of Gaussian space. We'll be thinking about the ambient, domain as Rn, and the distribution we'll be concerned with will be the standard normal distribution. And we want to think analogically to some kind of similar phenomenon, maybe to the CNF sparsification hold over Gaussian space. So okay, we want to analogize CNF sparsification. Well, we should start by analogizing CNFs. What should I think of as kind of a continuous analog of a CNF formula? So the way we kind of thought about it was like this. If you think about a Boolean clause, one of these ors that gets anded together, intersected to form a CNF formula, you can think of a clause as kind of chopping off a subcube of the Boolean hypercube. Chop off this subcube, this subcube, and you're left with a set of satisfying assignments of the original CNF, right? For instance, if I have a clause like this, x1 or not x2 or not x3, well, inputs that are in this subcube, starting with 0, 1, 1, and then anything will be chopped off. They don't satisfy that clause, okay? So in Gaussian space, the continuous domain, we can very naturally, I think of a half space as chopping off a region of Rn. So this is the first of many outstanding illustrations we'll see in the talk. I've drawn a half space for you here, and you can see it's chopping off the points kind of in the top right corner. Right? Those would be eliminated if you had a half space like this as sort of part of your analogous object to a CNF. The analogous object will be an intersection of half spaces. Okay? Okay, so let's push the analogy a little further. We can think about narrow clauses in the CNF setting, a clause of width w. Well, it chops off a 1 over 2 to the w fraction of the Boolean cube. If it's even narrower, it chops off even more of the Boolean cube. So I think the analogous way to think about this in the continuous setting is that if I have a half space, say it's u dot x less than or equal to w, where u is a unit vector, well, Gaussian space, this chops off the Gaussian tail e to the minus w squared over 2 or so fraction of the Gaussian space because of spherical symmetry, rotational symmetry of the Gaussian. Okay? So we have some kind of analogy here that analogous to clauses of width at most w are half spaces where the separating hyperplane has Euclidean distance at most w from the origin. Okay, we'll call such a half space, we'll say it has geometric width w. So far, so good? Okay, good. Good. So if you intersect a bunch of clauses, narrow clauses, you get a narrow CNF. If you intersect a bunch of narrow half spaces, you get something we'll call like a bounded width convex set. So we remember that every Boolean function, of course, you can write it in some way as a CNF formula. If you allow yourself enough clauses, maybe 2 to the n clauses, then you allow yourself arbitrary width. Okay? Well, analogously, every convex set in Euclidean space is expressible as an intersection of half spaces. You just take all the supporting hyperplanes. And again, we may have to allow half spaces to be very far from the origin, depending on what the convex set looks like. We may need infinitely many half spaces if the convex set is curved or something like this. Okay? So we have an analogy taking shape, and we'll say that a convex set has geometric width w if it's an intersection of half spaces where they're all distance at most w from the origin. So I think this is a reasonable analog of width w CNF formulas when we go to the Gaussian setting. Okay? Good. So this slide probably won't be much of a surprise. It's an exact kind of Gaussian space analog of the simple folklore Boolean fact that we saw earlier. Okay? If we have an intersection of S half spaces, let's go through it. If we have an intersection of S half spaces, then there's an intersection of fewer half spaces. Like Alexandros said, it's just going to be, we just get rid of some of the constraints, which is an approximator for the original intersection of half spaces, and our approximator has small geometric width. Okay, and again, for the rest of the talk, when I talk about approximation, I mean vis-a-vis the standard Gaussian distribution. So I've got one convex set, I've got another convex set. The way I measure the quality of the approximation is just looking at the Gaussian volume of the symmetric difference. Okay. And it's the same argument we saw before. Maybe you had infinitely, well, sorry, I don't have infinitely many constraints. I'm assuming that I start with just S half spaces. Okay? So I just do the same union-bound argument. I throw away every half space, every one of my constraints that's too far from the origin. Each one I throw away gets rid of at most epsilon over S fraction of Gaussian mass. I do a union-bound and I'm done. So we have this analogous statement to the kind of simple one-line observation in a Gaussian space, right? If I have an intersection of few half spaces, it's essentially a narrow convex set, a narrow intersection of half spaces, and there's probably not a lot of suspense associated with the next bullet. What about a converse result? Can we go in the other direction, the same way we did in the Boolean space with the CNF sparsification? Okay. So hopefully it's a reasonable question, or it feels like a reasonable question. The question, again, to state it explicitly, is suppose I come to you with a convex set of bounded width. This may be an intersection of infinitely many half spaces, right? But I do know that they're all at distance at most w from the origin. Okay? What I'd like, I'm wondering, is there an intersection of a finite number of half spaces? Again, maybe a number of half spaces that's independent of the ambient dimension, the way it was in the Boolean setting, which is close to k. I can get arbitrary closeness by adjusting my accuracy parameter. The question makes sense? This would be like an analogous phenomenon in the Gaussian setting. So I don't want to keep you in suspense. The answer is yes, something like this is true. We get a bound of 2 to the 2 to the w to the 4th over epsilon squared. And I'll talk more about the quantitative aspects of this bound as we move on through the talk. Okay? But, you know, the punchline, we can get sparsification in the Gaussian setting. So, you know, I think the way you should try to approach this kind of thing first is to do the simplest kind of thing. We thought initially about, can we do something like a packing covering argument, some kind of very simple thing, the way that the initial results in the Boolean setting work, something like this result due to Luca-Trevisan. We weren't able to make it work, and it turned out the route where we were able to get to the destination went through this famous majorizing measures theorem about Gaussian processes. So I'm going to talk about Gaussian processes now for a bit. Okay? Okay. So what's a Gaussian process? Well, a Gaussian process is just a collection of jointly Gaussian random variables. This is the way I encourage you to think about it. We've got this index set, which I'm writing capital T. It might be infinite, it might be uncountably infinite, but the property is if you take any single one of these random variables or a finite linear combination of them, it's distributed as a Gaussian. Just think of it as a high-dimensional Gaussian. Big, you know, vector-valued, infinite-dimensional, perhaps, random variable where each constituent real component is distributed as a Gaussian, a jointly distributed high-dimensional Gaussian. Okay, and we'll say a Gaussian process is centered if each one of these individual Gaussian components has mean 0. So far, so good? Okay. Good. So So a nice thing about centered Gaussian processes is that they correspond exactly to sort of an underlying geometric set. So I encourage you to think about just, finite dimensions. So you've got some finite set of vectors in Rn, these v sub t's, okay? A collection of vectors like this defines a Gaussian process. For each of my vectors, I take the inner product of that vector with a standard Gaussian, and I got some Gaussian random variable out. I have another vector, I get another Gaussian random variable out. Maybe these two are correlated, these two would be independent, depending on the vectors, so on and so forth. So we'll say that given any set of vectors in Rn, think of it as in Rn, there's associated with this set of vectors a standard Gaussian process. We'll call this the canonical Gaussian process. It turns out that any centered Gaussian process can be viewed as a canonical Gaussian process. We'll be thinking, I encourage you to think in this talk about the case in which this underlying index set is finite, but all the results I'll tell you about go through in the infinite case. There's no restriction about finiteness for the results I'll tell you. Okay? Good. So Gaussian processes like this are extremely nice because they just, if you know everything about the geometry of the underlying index set, you know everything about the Gaussian process. Okay? If I've got a centered Gaussian process corresponding to this collection of vectors, the dt's, well, to tell you everything there is about the Gaussian process, we just need to understand the covariance matrix. The variance is trivially just this squared length of the underlying vector for a given element of the process, and the covariance, again, is just the inner product. Okay? So thinking about these Gaussian processes is the same thing as thinking about the geometry of the underlying set of vectors. So that's kind of nice. Okay. So Gaussian process, this big, complicated, high-dimensional random variable. We often want to think about something simpler. In particular, we're often concerned with the supremum of the Gaussian process. This is just, you make a draw of the entire Gaussian process, you output the index which had the largest value. Okay, so it's just a single real random variable, but it's kind of complicated. It's the supremum of all of these jointly distributed correlated Gaussians. Okay, so this has been widely studied by many people. It has many applications across different areas. What does this have to do with the question we were talking about a few minutes ago of approximating convex sets? Well, I'll give you a pretty superficial answer to this, but hopefully it's still somewhat convincing. Suppose you have a convex set that contains a ball around the origin. Okay, so at the origin, you've got some convex set containing a little ball around the origin. It's defined by a bunch of separating hyperplanes supporting half spaces, and they all have this form. Some vector v dot x is less than or equal to 1. I can write all of my separating hyperplanes in this way. Well, if I make a draw from the underlying Gaussian that kind of gives rise to the coordinates of the Gaussian process, that draw lies outside of a single half space, if it violates the defining inequality for the half space. And similarly, a draw like this lies outside of the entire convex body, the entire intersection of half spaces, if the supremum of this Gaussian process corresponding to these vectors is at least 1. Okay? So hopefully this convinces you that there's, kind of a very close connection between convex sets, if you're thinking about, the ambient distribution over Rn as being Gaussian, and the supremum of a Gaussian process that's directly associated with these convex sets. Okay? So we're motivated to think about Gaussian processes. Okay, one more piece of terminology, then I can tell you the results. We'll say that the width of a Gaussian process is just the expectation of its supremum. It's kind of the scale at which things are happening for this Gaussian process, the typical value of the supremum of the Gaussian process. So, roughly speaking, this has something to do with how complicated or rich the set is. Let's look at just one or two examples to get some feeling for this. Here's a first very simple example. Suppose you've got some index set capital T, and the vectors are just orthonormal unit vectors. So you've got capital T, many perpendicular vectors to each other, unit vectors. Then the expectation of the suprema, the width of this Gaussian process is just square root log T. And we understand everything there is to understand this, just a very standard fact about the supremum of a bunch of independent Gaussians. Square root 2 log, whatever it is, square root 2 log n, something like that. So that's great. On the other hand, you can have a very large set of vectors. You can have infinitely many unit vectors. If they lie in a low-dimensional subspace, say a d-dimensional subspace, then the width of that Gaussian process will be small. It will be at most square root d. Okay, so think about you've got like a d-dimensional space. Maybe I've got my index set contains every vector in this d-dimensional subspace. Okay, well when I make a draw of G, right, what's the maximizing vector, the vector that's going to have the largest inner product with G? It'll just be the unit vector pointing in whichever direction G happens to go in. right? And so now it's trivial. You say, okay, what's the inner product between g dot g, normalizing by the length of g? This is just a distribution from the draw from the chi distribution. Right? The square root of the length of d squared summed independent Gaussians. So we'll get square root d in this case. Okay? Just building a little intuition. But of course, things can be more complicated, right? Maybe I have an index set where each of the vectors has a substantial component in the same direction. And then there are, all these other different orthogonal directions where you have a smaller component. Now it's going to depend on how these parameters play against each other, d versus the number of vectors in the set, and so on and so forth. And of course, in a general Gaussian process, we might not just be dealing with unit vectors either. I might have long vectors, short vectors, correlated vectors, so on and so forth. So it can be a little complicated. Okay? But hopefully we're getting some feel for kind of these Gaussian processes. Okay, so now I can tell you about the main result. The main result is sparsification for this random variable supremum of a centric Gaussian process. So let's go through it in some detail. I come to you with any set of vectors in Rn, this index set capital T. It might be infinite, it might be uncountably infinite. It is what it is, okay? It should be, the vectors, they should be at least bounded though, or else you'll have an infinite supremum. Good, so I come to you with this set of vectors in Rn. I think about the corresponding centered Gaussian process, right? I've got a Gaussian for each vector, this big jointly correlated collection of Gaussians. I want to do some kind of epsilon approximation of the Gaussian process. I want a simpler random variable, which is close, maybe in an L1 sense, like we have here in the equation, to the original random variable, supremum of the Gaussian process. The theorem tells us that we can do this. There's a finite-sized subset, a constant-sized subset, if epsilon is constant. So size, it's the set capital S, 2 to the 2 to the 1 over epsilon, many vectors. So there's a finite set of vectors, and an appropriate collection of offsets, these real numbers C, such that if I take the Gaussian process corresponding just to the vectors in this finite set S, and I shift them appropriately by these constants C, and I look at the supremum of that much smaller Gaussian process, it'll be kind of epsilon accurate vis-a-vis the original Gaussian process. So remember, this W of t is just the width of the original Gaussian process, the expectation of the supremum. So I'm approximating this random variable, supremum of the Gaussian process, at the right scale, at the scale of its expectation to this kind of epsilon accuracy. Okay? And the main thing we should take away from this is that the subset of vectors we use is a constant size. It doesn't depend on the ambient dimension n. It doesn't depend on the number of vectors defining the Gaussian process, the dimension. It might be infinite, it's fine. Okay? However, one thing we should note here is that this approximator, this new Gaussian process we're using, just defined by the index set S, is not centered. We had to have these shifts, these offsets. And you can show, in fact, that that's inherent. You can't have a result like this without the offsets. Okay? So I want to tell you about a number of consequences of this result. And I'll try to, in the upcoming slides, it'll be red to kind of indicate what's new on each slide. Okay? So what's new on this slide is multiplicative approximation. And I have to make an extra assumption. I have to assume that the underlying index set of vectors is symmetric. If I have a vector v in the set, I also have minus v in the set. Okay? So what this result says, we lose a little bit quantitatively. Now the approximating set is size 2 to the 2 to the 1 over epsilon cubed. But now we're getting kind of a, I don't know, you could say like a relative error approximation to the supremum of the Gaussian process. So I've got this small set of, this small sparsified collection of vectors, such that for 99% of the draws from the original Gaussian process, if I make the corresponding draw from my smaller, non-centered Gaussian process, it will be multiplicatively accurate. Okay? In some sense, this shouldn't be that surprising that you can get something like this. I mean, if I'm approximating a number like 1 by a number like 1.01, well, that's multiplicatively accurate as well as being additively accurate. The only case where, something like that doesn't work is if I'm approximating 0.01 by 0.02, that's no longer multiplicatively accurate. So the way you'd hope to prove something like this is by showing some kind of anti-concentration result for the original supremum, anti-concentration around 0. You're not too likely to take extremely small values, and doing that is what costs us kind of the extra factor, the reason the bound is a little quantitatively worse. Okay? There's a high-level sketch, of course. Okay, so we can get multiplicative approximation in the case where the underlying process is symmetric. We can also change things and get a centered approximation in the symmetric case. So again, I'm assuming that the underlying set of vectors is symmetric. I'll now give you a symmetric set of vectors And you notice that now this Gaussian process that I'm using for my approximation is centered. It no longer has these constants. So the intuition, getting rid of these constants, these constants we saw in the denominator down here, shouldn't be terribly difficult because again, like we kind of know how to approximate constants using the supremum of a Gaussian process. If I make enough draws for my bunch of independent Gaussians, I get concentration of what the supremum is, okay? But then this does lead to, you'll notice if you're looking closely here, my approximation is over Rn prime. I may need to introduce some fresh dimensions in order to have these new Gaussians which let me simulate the constants kind of thing, okay? But bottom line, we're doing now approximation when the underlying index set is symmetric, using a symmetric set of vectors, and it's centered, my approximating Gaussian process. I no longer need these constants. And the reason I'm interested in doing something like that is because if we rephrase this result, we can phrase it in kind of a different, maybe interesting way, that norms are essentially low dimensional. So just a standard fact, if I come to you with a norm over Rn, we can write it as the supremum of a bunch of linear forms taken over a symmetric index set of vectors. It's just one way to think about what norms are over Rn. Okay? No, I shouldn't call this a theorem. I shouldn't even call it a corollary. It's just a restatement of the previous slide's result. So I come to you with an initial norm over Rn. I want to approximate it. I'm going to approximate it by another norm. So the initial norm is phi. The approximator is psi. And I can give you an approximator where on 1 minus epsilon fraction of draws from the Gaussian distribution, the approximator has very high quality in a relative error sense. It's multiplicatively 1 plus epsilon accurate. Okay? And crucially, the approximator, the psi, is kind of a junta. It depends only on a constant number of dimensions in Rn. Okay, so kind of a tagline for this might be that every norm is close to a junta over Gaussian space. Okay, we found this a little counterintuitive, so maybe I'll spend 2 minutes or 1 minute on looking at an example of this. Suppose you start with just the standard Euclidean norm over Rn. You might say, oh, this doesn't look like a junta. It depends on every direction. In some sense, it's like tragically junta-like, right? Over Gaussian space, the standard Euclidean norm is essentially a constant. It always gives you square root n, essentially, right? And so I can approximate that constant. I don't need n Gaussians to approximate that constant. I can approximate that constant square root n by an appropriate scaling. I'm looking at a supremum of just constantly many Gaussians. You work out the math with the variance of the concentration of the supremum of independent Gaussians, and this will be an epsilon approximator on epsilon, all but epsilon fraction of inputs. Okay? So it's kind of weird. We're approximating this thing which is actually a constant by a different constant in kind of an awkward way. Okay? So this seems to check out. Kind of a second silly example, if I come to you with a norm which is the L1 norm over 2 particular directions, well, that's already a 2 junta, right? No approximation required. Just depends on x1 and x2. Okay. So far, so good? Good. Okay, moving on. So we are also able to establish the kind of motivating result that I started off talking about, sparsification of these low-width convex sets. And I'm not going to go over this in detail. It's just exactly the thing we were talking about originally. You come to me with any convex set, which is an intersection of half spaces at distance at most w from the origin. You can use a finite number of half spaces, depending only on w and epsilon, and get an epsilon approximator of it as an intersection of that many half spaces. Okay? And this takes a little work, but I'm not going to go into it. Okay. I want to spend a minute telling you about a couple of applications from theoretical computer science, which is kind of the tribe I come from. So maybe to simplify this a little bit, I encourage you to ignore the word agnostic everywhere. This is just an old background result which says, hey, imagine you get random examples drawn from the Gaussian distribution, which are labeled examples, okay, in the sense that you press a button, you get an n-dimensional vector in Rn, and you get a bit. And the bit tells you whether or not that point in Rn lives in some convex set. There's like an unknown convex set. You want to learn the convex set in this, Gaussian distribution sense from random examples drawn from the Gaussian distribution labeled according to whether or not each of the examples is in the convex set. So you want to learn convex sets like this in the Gaussian setting. Okay? This old result says you can do it using 2 to the square root n samples. It's based on Hermite concentration of Gaussians, blah, blah, blah. It's known to be optimal. You can't do better than 2 to the square root n in this Gaussian setting for this convex set learning problem. Okay? Old result. So now we're going to specialize. It turns out that using this technology, being able to approximate small width convex sets, if you have an extra assumption, if you know that the unknown convex set you're learning has bounded geometric width, it's an intersection of half spaces that are all W close to the origin, then it turns out you can learn with many, many fewer examples. You can learn with just a polynomial number of examples if the width is constant and this accuracy parameter is constant. Okay? And this is really done just by plugging the new sparsification result into some other result from this old paper. It turns out that in the standard setting, if your convex set is not an arbitrary convex set, but it's an intersection of a small number of half spaces, you can do much better than learning an arbitrary convex set. And well, what do we know now? We now know that if I have bounded geometric width, I'm quite close to an intersection of a small number of half spaces. So you just combine these two results and you get the new statement. So we go from kind of this mildly exponential complexity in the general case to polynomial complexity if the geometric width is small. Make sense? Okay. So the next slide is another application, one which I'm really kind of annoyed about because I've been working on this problem for a long time and I can't solve it. Has to do with testing whether an unknown set is convex. So this is a little bit of a different framework. Again, forget this word tolerantly, keep it simple. Imagine there's an unknown set in Rn. It could be any set in Rn. Okay? You have black box oracle access to this set. You have a box where you feed in a vector and it outputs a 0 or 1, telling you whether or not that vector is in the set. Okay? Your goal is to interact with this box and figure out distinguish between the following two alternatives. If the function that the box has inside it, the subset of Rn, is convex, you should say convex. I plugged in a couple of inputs, saw some outputs, decided it was convex. If the function or the set that's inside the box is far from convex, it has distance epsilon from every convex set under the Gaussian measure, then you should say not convex, far from convex. So this is the so-called property testing problem for convexity. Right? We want to interact with a black box oracle for an arbitrary unknown set, not too many times, and be able to distinguish between the case where it is convex versus it's far from convex. We don't understand the complexity of this problem. Our lower bounds are like log n, tragically. Our upper bounds are 2 to the square root n. So there's a big gap here. And I'm telling you in this slide about the upper bound. It turns out the best we can do for this problem is like a learning-based approach, the same kind of thing from the previous slide. So if you want to test whether an unknown set is convex, tragically the best we can do is 2 to the square root n interactions with a box like this. And using this new sparsification thing, we can test kind of a subclass of convex sets using just a constant number of queries. So, now my goal is that if the set is a geometric width W convex set, I should say convex, geometric width W convex. If it's far from every geometric width W convex set, I should say far. We can solve that testing problem with just a constant number of queries if W is constant. Okay, and this is done using recent results of Anindya, Alkanan Mosel, Joe Neiman on kind of this testing problem. It turns out you can efficiently test this other class of functions, whether something is an intersection of half spaces or far from an intersection of half spaces. And now we know that kind of, having small geometric width is like, we can relate it to this property of being an intersection of half spaces. Okay, so again, we go from kind of very bad complexity in the general case, 2 to the root n, to constant complexity in the special case where the width is constant. Okay? Okay. Let me say just a little bit about the quantitative aspect of the result, and then I'll spend the rest of the talk telling you something about ingredients in the proof. So we've been seeing slide after slide after slide, the size of our approximating sets are always 2 to the 2 to the something, 2 to the 2 to the 1 over epsilon, 2 to the 2 to the 1 over epsilon cubed, whatever. Doesn't look that great, right? Maybe we can improve this quantitative bound. Is this bound, good? Is it not so good? If you remember, in the Boolean setting, these optimal results that were achieved by Levet, Wu, and Zhang are 3 exponentials lower than 2 to the 2 to the 1 over epsilon squared or whatever, right? They're, for constant width, those results were like log 1 over epsilon to the W. So polylog 1 over epsilon, our results are 2 to the 2 to the poly 1 over epsilon. So we seem to be off by 3 exponentials. That's not so great, but it turns out we're off by at most 1 exponential. So you can argue that the only way to do this kind of approximation, is that you need at least 2 to the 1 over square root epsilon many sets. You can't hope for polylog 1 over epsilon. You can't hope for poly 1 over epsilon. We don't know whether the right answer is sort of singly exponential in 1 over epsilon, 1 over root epsilon, or doubly exponential in 1 over root epsilon, but we're not off by 3 exponentials. We may be off by 1 exponential, of course. Okay. Okay, so for the rest of the talk, I want to tell you about some of the ideas in the proof of the main theorem. So just to remind you what the main theorem says, again, I come to you with an arbitrary index set, collection of vectors in Rn, defining a centered Gaussian process. The main result says that there is a non-centered Gaussian process, which is kind of a subset of this original set of vectors, which is of constant size, finite size here, and the kind of non-centered Gaussian process over my subset is a high-quality approximator for the original Gaussian process. Okay? Again, at the scale of the Gaussian process, relative to the expectation of the supremum. Okay. So the first thing we're going to do is get rid of one annoying parameter and just rescale all the vectors so that the width of the Gaussian process, the expectation of the supremum is 1. Okay? So saying the goal again then, we just want to come up with a small subset of vectors and a collection of real numbers, the small subset to the 1 over epsilon or something, such that I'm off by at most epsilon when I look at this simplified, sparsified Gaussian process. Okay? So that's what we'd like to do. What's the first thing you might think to do? Well, I've got this big, crazy cloud of points in Rn, and I want to get a much smaller subset of points in Rn, so maybe I should do some kind of clustering or something and take representatives from each cluster. That's the first thing you might think about trying. Okay? So let's cluster in such a way as to create a delta covering of the vectors. So here's another high-quality illustration. Maybe this is my collection of points, and I cover them with delta radius balls. So this cluster, this cluster, this cluster, this cluster, I cover all the balls. Cover all the points. Okay, say that I have m clusters by doing this. It costs me m clusters, and m is maybe the best number of clusters I can have. So these clusters, C1 through Cm, they cover all the points. Well, I should, maybe just take one point within each cluster. Seems like a natural thing to do. So I'll choose an arbitrary vector, call it R of S within cluster S. These are like the yellow points I want you to have in mind. They could be anywhere. It doesn't matter if they're in the center, off to the side, or whatever. Okay? Okay. Good. So I've got my M clusters, C1 through Cm. I've got a representative vector for each cluster, R sub S for cluster, V sub R sub S, V sub R of S for cluster S. This line is trivial, right? I'm saying that if I just look at one cluster and I look at the supremum of, kind of the Gaussian process corresponding to just the vectors in that one cluster, well, I took out, G, product of G with V of R of S, and I shifted it to the other side. I didn't do anything in this line. This is a triviality, right? But we see that this is just a single Gaussian, and this is some kind of number. This is a simplified Gaussian process. It's kind of a wimpy Gaussian process, though, because each of these vectors, V minus V of R of S, is like a short vector. Right? So this is, I've expressed the original Gaussian process over one cluster is just a single Gaussian plus the supremum of kind of a low variance, a low heft Gaussian process. Okay? So you would think, oh, this shouldn't, you should be able to approximate that kind of small, low variance Gaussian process with something like just a single number, and indeed, of course, we can do this, right? So what are we saying here? We're saying that if I look at a collection of vectors, these W sub t's are like those shifted V minus V R of S vectors. If each of the vectors has small norm, then it's unlikely that just taking the Gaussian process corresponding to the supremum of the original Gaussian process, it's unlikely that you get an outcome that's far from the mean, okay? And, you have this strong tail bound that gives you a bound on variance, and this is just a consequence of Gaussian concentration inequality for Lipschitz functions. This is not a hard theorem, hard result. Good. So what are we doing? We'll zoom back out. We have a covering using M clusters. We have a representative vector from each cluster. Okay? For each cluster, the kind of sub-Gaussian process there is like one Gaussian plus this sort of wimpy Gaussian process. And this easily gives us that we get a high accuracy approximation for the supremum of, the supremum of the process restricted to just one cluster by replacing, this last supremum with just a constant corresponding to its expectation. So for one cluster, we can do a good job by just, using a single Gaussian and a shift. Okay? Okay, this looks potentially promising. I'm I'm just saying the same thing as before on the last slide. Right? We can get a high accuracy approximator for one Gaussian, for the Gaussian process on one cluster with just a single Gaussian and a suitable shift. That's good. Great, so we're going to replace, Gaussian process over this cluster by single Gaussian and shift. We'll do it for each of the clusters. Okay, I'm saying the same thing multiple times here. Right, so given that I have this clustering with m clusters, it's natural to say, oh, maybe the way I approximate my entire Gaussian process is just by doing this for each cluster. I'll have m Gaussians, I'll have, like a sparsified process of size only m then, with m corresponding shifts. Maybe I'm done. Right? If I did this, I would have m as the dimension of my sparsified process. That would be great. How good would it be? What would the error be?
Yeah, but also, like, having one the size of m could be large.
M could be very large. Yeah, we're going to have to confront both these kinds of issues. The error and the size of the approximation, exactly. Yeah. Okay, so within a single cluster, we saw we have error delta. And we're saying for now we have m clusters. So if you're a pessimist, you might be like, oh, maybe the error is going to be delta times m. It's not this bad. It turns out that the error is going to be at most delta square root log m. And you can show this essentially using Slepian. The worst case would be having some kind of orthogonality. And even in that case, it would just, the error would just scale like delta times square root log number of clusters. So maybe this looks promising. You might think, oh, maybe we're in business and we can be done quickly here. So what is this error? How is this error? Right? Well, obviously it depends on the relationship between m and delta. If m is not too big compared to delta, if it's less than sort of 2 to the 1 over delta squared, then by making delta smaller and smaller, I make the error go down to 0. And I can, I want to achieve epsilon error in the end. I choose a suitable delta so that it would work out and I would be done. This would be great. This is an easy case. Okay. What about a nightmare case? Could m be really large, like asymptotically bigger than 2 to the 1 over delta squared? Well, it turns out this can't happen, and this is just a consequence of Sudakov minoration. Okay, if the smallest delta net for my collection of vectors has size m, then the Sudakov minoration tells us that the expectation of the supremum is going to be at least delta square root log m. Okay, but we're in this setting, we kind of normalized, we set things up in the beginning so that the expectation of the supremum is 1. Okay? So that can't happen, right? It can't be the case that m is like asymptotically bigger than 2 to the 1 over delta squared. We know this is not going to happen. So, oh, good, it looks like we're close, but we actually are not close, right? It's possible that maybe in general m is something like 2 to the 1 over delta squared, and I would be getting constant error here, maybe error 1000 or something, and the original scale was 1 for the answer I'm trying to get. I want error epsilon. This can happen. There are actual Gaussian processes. It's easy to construct them, where at every scale, the best covering has size 2 to the 1 over delta squared. So we're not done. We don't have like a, there is this intermediate case. It's like the opposite of a Goldilocks thing. It's like being right in the middle is the worst possible thing, and it's a real phenomenon that can happen. Okay? Okay. So that was kind of an attempt to solve the problem by clustering at one scale. Natural thing you would think to do is maybe you can do some kind of clustering at multiple scales. We shouldn't just be putting all our eggs in this delta ball basket. We have to think about different possibilities. Excuse me. And if you're thinking about clustering at multiple scales, this probably brings to mind the idea of this majorizing measures kind of technology. And that's kind of the heavy hammer which we use to make things work. So there are many ways to kind of phrase the majorizing measures result, most of which I can't state in a reasonably coherent kind of way, but I'll try to say it in a way which I think hopefully is digestible for everyone to understand. So it's in terms of this notion of admissible sequences. An admissible sequence, so we start off with a set of vectors, this cloud of points and a bit is in Rn. We're going to think about an admissible sequence. What is an admissible sequence? It's like a hierarchical clustering. It's a collection of partitions of this set of points, where we start with the initial coarsest possible partition. A0 is the initial partition. All the points are in one cluster. Okay? And A1 is a refinement. We're going to break A0, that one cluster, into multiple pieces. A2 is a refinement of that. We break each of the pieces in A1 into subpieces, so on and so forth. Okay? Moreover, we have this bound. An admissible sequence is one where we have a bound on the number of pieces in the nth level of the partition. At level n, you have at most 2 to the 2 to the n pieces in the partition. I think there's a picture. So yeah, here at level 0, all the points in the cloud, all the points are in the one cluster. 2 to the 2 to the 1 is 4. So at level 1, you have the collection of all the points is broken, partitioned into 4 pieces. 2 to the 2 to the 2 is 16, so you'd have a total of 16 pieces. At most 16 pieces down here at level 2, 2 to the 2 to the 3, you have 256 pieces down at level 3, so on and so forth. A collection of successive refinements, partitions like this, is an admissible sequence. Okay? Okay, and we need one little piece of notation, which is if I give you a particular element, a particular vector, call it t, I'll write an sub t to indicate the piece of the partition at level n that that vector lies in. So there's one particular point, t, that I'm interested in, and it's in the original cloud because it's in the collection of all the vectors, of course. Maybe it lives in this piece of the 4 pieces at level 1. Maybe it lives in this piece of the 4 pieces at level 2. So just some notation to capture, kind of track where a given element goes as we successively refine. Okay? Okay. Good, now we can state the majorizing measures theorem. So this is kind of the hard direction due to Talagrand. It essentially says that if someone gives you any centered Gaussian process with a finite supremum, okay, there is a clever choice of an admissible sequence which characterizes the expectation of the supremum. There's an upper bound as well, due to Fernique, that's earlier, not as difficult. So let's drill down on this. I think this is called the gamma 2 functional or something on the right-hand side of this for this partition. If someone comes to you with the right, cleverly chosen admissible sequence, the expectation of the supremum is going to be lower bounded by this quantity defined in terms of the admissible sequence. So what does it mean? It means that no matter which vector you start with in your set of vectors, you trace its way down through that tree, and at level n of the tree, you look at the diameter of the piece of the partition that the vector lives in at level t, multiply it by 2 to the n, take the infinite sum as you go down this partition, okay? For the right admissible sequence, that's a lower bound on the expectation of the supremum. The other direction I didn't write down tells us that for every admissible sequence, this is an upper bound up to constants on the expectation of the supremum. So these admissible sequences, the right admissible sequence captures the expectation of the supremum. Okay? Okay. Good. So if you look at this, this looks very promising, right? Intuitively, what do I know? We're in the setting, the way we set things up, this expectation of the supremum, the Gaussian width, the left-hand side is 1, okay? So I have that 1 is at least this sum, this infinite sum of 2 to the n over 2 times the diameter of the piece that the element t lives in for any element t. So intuitively, like it feels like, oh, these diameters have to be going down at least as fast as 1 over 2 to the n over 2, because if they were not going down as fast as 1 over 2 to the n over 2, I'd be adding up a bunch of 1s, and there's no way that that could be a lower bound on the left-hand side, which is just 1. Right? So heuristically, it feels like we're in quite good shape here, right? The number of pieces at this nth level we know is at most 2 to the 2 to the n. So remember the error that we said we can achieve is the diameter of this piece, the diameter of the piece times square root log of the number of pieces. Well, if those diameters were really going down like faster than 2 to the minus n over 2, I know that the m is 2 to the 2 to the n, I'd be getting something much less than 1 here. And it looks like it should work. If you had kind of a uniform rate of decrease, this would work, we'd be done. That doesn't happen, it provably doesn't happen. So there are Gaussian processes you can write down. It's related to the phenomenon I talked about earlier, where at any fixed scale, clustering at that scale is not going to work. So you have to do something a little different, but it's not difficult. I'm not going to do it. It's a little bit involved. There's a calculation, but you can